Assalamu alaikum. Now, last time we discussed the form number 4. The topic same first order linear differential equation. We discussed the form number 4, exact differential equation. Now, in the sequence of exact differential equation, the next form is non-exact form by non-exact differential equation. Generally, non-exact differential equation or identified by linear differential equation. You can say non-exact or linear differential equation. The identification of non-exact, the partial derivative conditions is not satisfied because in situation of exact, partial my is equal to partial n with respect to x, and in situation of non-exact, partial derivative n with respect to y is not equal to partial derivative n with respect to x. So identification of non-exact, if this partial derivative condition is not satisfied m with respect to y and not equal to n with respect to x, first write the equation in standard form m dx plus n dy is equal to 0 and check the condition. If equality hold, then follow the exact method technique, and if the condition is not satisfied, so we follow the linear differential equation. After the failure condition of partial derivative, the general form of linear dy by dx plus p of x y is equal to q of x. After failure equation of the partial derivative, write equation in this standard form, the operator dy by dx, then p of x means function of x, then y power 1 is equal to q of x. So first of all, write equation in this form. Equation can be written in this form. So this is considered as linear differential equation. Now the topic is first order linear differential equation, then again linear. So this the main topic of linear means we are considering the first degree equation. But here linear means with respect to algebra. Linear in y power y. So with respect to algebra, this equation identified by name linear means y power 1. If not y power 1, so this equation is not considered as linear. Sometimes if equation is not maintained, the operator dy by dx, so we try to maintain the equation in dx by dy. We change the dependent and independent variable, then dx, dy, then function of y, then x power 1, then function of y. So that form considered as linear in x with respect to algebra. Some rare situation we follow the alternate form in which we change our dependent and independent variable. Dx, then function of x, function of x. If you change the operator dx upon dy, then function of y, then x power 1. But here y power 1. So this is the standard form of linear differential equation. Now the solution of different linear differential equation is not follow the pattern of the non-exact differential equation. We follow the directly the solution general form, multiply equation by e power integral of dx. multiply each term by e power integral e dx. E is a function of x. So multiply whole equation integral dx or plus p dx dy by dx, then e integral e dx, then dx y is equal to e integral dx, then b of x. Now observe the left hand side expression. Left hand side expression maintain the derivative formula u into v in reverse form. Because of the exact, you recall the definition of exact differential equation, we find the function whose derivative is given to you. So in this pattern, the left hand side expression always maintain u into v formula, in which u is our multiple function e power integral p dx, and the v function is y, dependent variable. So you can write d by dx bracket e power integral p dx and y is equal to e dx then dx, or missing the term 2x also है q of x, q of x. Now check derivative of these two functions. First function u as it is, derivative of y with respect to x dy by dx, then plus y function as it is v, and then derivative of this. So derivative of exponential function as it is, and further derivative of power. The power involves integral of p dx, and the derivative of the integral is the original function px. If you integrate, then you will get this. If you differentiate, then you will get px dx. So just like the derivative of e power x square is equal to e power x square into multiply derivative of x square is 2x. So in a similar pattern, derivative of this as it is, and then further derivative of power integral of p dx is equal to px. Integral and derivative are antiderivative cancel, so you get original function. So left hand side expression always maintain u into v formula, where u always e power integral p dx and v always y in case of this general form, which is linear equation in y. The alternate form of this linear is dx dy is equal to p of y, x power 1 is equal to q of y. Then in this general form we write x instead of y. The same e power p dx, then multiply x, not y. V is always dependent variable. In case of dy by dx, y is dependent variable, but in rare situation, case of dx over dy, we consider x as dependent variable. So in general, u always e power integral p dx and v always dependent variable. In case of dy by dx, y, v is equal to y. In case of dx dy, v is equal to x. So you just directly write this expression after multiplying this factor directly u into v formula, u always this, v always this, y. You can check easily the derivative of this is equal to this. So we use u into v formula in reverse order. Generally we find dy by dx, u into v is equal to u dv by dx plus v du by dx. But here we use the expression of u dv by dx plus v du by dx is equal to d of dx u into v. The same formula in a reverse order. Now, just equation after this u into v formula is separable variable form d of e dx y, then qx e dx, then dx, and then just integrate. So after this integration, differential of this just e dx, then y, and then after integral, in case of particular values of qx and t, you can easily integrate, then plus c after integration, c as arbitrary constant. So this is our final solution. Now this step like this: integral of dx x, integral of dy y, integral of d sin x sin x. Similarly, integral of d e power p dxy is equal to e integral p dxy. Now this e power p dx is called integrating factor. This e power integral p dx is called integrating factor, or in short we write I dot f. So this factor is important, from which you can easily basically integrate. So that is why this is known as integrating factor. So this is how you find the solution of linear differential equation. This is the general solution. Now we consider the particular problem and how to find the solution. Not following this exact solution situation, because this involves the function as p and q, which is not defined. But in particular problem, p and q defined, so you can easily first find the integrating factor by integral e to the power e p dx, then multiply whole equation, then left hand side become u into v formula, and then finally integrate. So you can easily find the solution of linear differential equation, or the alternate form of the non-exact. So if equation non-exact, then you try to solve by linear differential equation. So consider a problem. For example, x plus 1 dy by dx minus y is equal to dx x plus 1 whole square. The equation is not the standard form of linear. Again, they follow from the first form. Equation is not separable variable because y shift to the right hand side, then function of x plus y cannot be separated. So they both terms are disturbed with respect to dx and dy. You cannot write this equation as function of x dx then plus function of y dy. Then what about the homogeneous? The function is not homogeneous because of the transcendental form of the function. E power lambda x cannot be separated as lambda is common. So not satisfying the homogeneous condition, and in general you can say the non-homogeneous, but this is not a standard homogeneous differential equation because standard non-homogeneous consists of the multiplier of dx dy expression only involving with degree 1 x power 1 plus y power 1 plus constant. Similarly, x power 1 y power 1 plus or minus constant. Not only x, maybe 2x or 2y or 3x minus 1. Now we follow the form number 4 in which the exact situation satisfy. So first consider the terms of multiplier of dx and the terms of multiplier of dy, so that you can find first capital N, and then their exact situation. So you can write easily like this, just to understand the failure situation. Dx multiply this factor, so you can write this as dx x plus 1 whole square, then plus y. Dx multiply this, dx multiply this. So these both terms involve a multiplier of dx. Consider as right hand side, and one of the term consider as negative because left hand side is equal to right hand side. You can shift left term or right term, so we shift left term as minus or plus. Consider minus x minus 1 as dy is equal to 0. So this is a standard form of exact differential equation. M then n. Now m y is equal to 1, derivative x 0, y 1, and with respect to x minus 1. So I show you the failure situation. Equation is not separable variable, is not homogeneous, is not non-homogeneous, our standard form, and equation is not exact because 1 is not equal to minus 1. So this is our situation to follow the linear form number 5. Our equation is not in standard form of linear. First, after multiplying or divide or just shifting to the left or right term, just in single step you easily write equation in standard form. So first dy by dx term, dy by dx, this multiplier term is involved as a multiple term which is not standard. Our dy by dx to constant coefficient, to divide whole equation by this factor minus 1 upon x plus 1, then y, then divide this factor involved as dx just x plus 1, because x plus 1 whole square divided by x plus 1 cancel factor. Now this is a standard situation because of dy by dx, then plus dy by dx, consider plus sign, then minus here as p of x, then y power 1, and then q of x. Again I repeat, dy by dx, then plus function of x, y power 1 is equal to function of x. If right hand side involve any function of y, then equation is not considered as linear. Right hand side only function of x, and left hand side involve dy by dx plus function of x, then y power 1, not y square, because of linear in y. So this is our p of x. Our requirement to find p of x, which involved as integrating factor. So first find integrating factor, e integral dx dx, e integral minus 1 upon x plus 1 dx is equal to e minus log x plus 1. Then the property of logarithm, the multiple change into power, so log x plus 1 power minus 1, then log e cancel, then x plus 1 power minus 1, you can write 1 upon x plus 1. So this is our integrating factor. Now the solution technique, original equation multiply by integrating factor, which is equal to 1 upon x plus 1. Multiply original equation by 1 upon x plus 1. 1 upon x plus 1 dy by dx minus 1 upon x plus 1 whole square. One upon x plus 1 already involved, so 1 upon x plus 1 whole square is equal to, again divide, multiply 1 upon x plus 1, so this x plus 1 cancel out. First term multiply 1 upon x plus 1, then second term multiply 1 upon x plus 1 whole square. Then right hand side, in our third term involving x plus 1, then multiply 1 upon x plus 1 or divide x plus 1, so x plus 1 cancel out, we get this factor. Now maintain this u into v formula. U into v formula, d by dx, just like in general form, integrating factor, then multiply dependent variable y, then ex. Left hand side expression always maintain u into v formula, where u is equal to integrating factor and v is equal to y, dependent variable. You can easily check u as it is, derivative of y dy by dx, y as it is, derivative of 1 upon x plus 1. How to find the derivative of 1 upon x plus 1? You consider this 1 upon x plus 1 as x plus 1 whole power minus 1. Then the derivative of algebraic expression, power multiply minus, then x plus 1, then power minus 1, minus 1, minus 2. So you can write this as minus 1 upon x plus 1 whole square, minus 2 change into plus 2. So this is exact derivative of integrating factor. factor or derivative of u, y as it is. Minus sign is also maintained. Now the separable variable form, differential of x plus 1 multiply y dx dx, separable variable form. So linear directly convert into separable variable form after multiplying integrating factor and left hand side maintained as exact differential of u into v, u always integrating factor, v always y in case of dy by dx, or v is equal to x in case of dx by dy. Left hand side integration just original function x plus 1 y, just like integral of dx x is equal to integral of ex plus ex and c constant of integration, or you can write this y plus ex plus c multiply x plus 1. This is our final solution of linear differential equation. Now I will introduce some practice problem. Problem number 5. dy by dx 1 upon x squared is equal to x cubed minus 3. Similarly, dy by dx plus y cot x is equal to cos x dy by dx y tan x cos of x dy by dx minus y is equal to e 2 of x y minus 3x dx plus x dy equal to 0. So majority of the equations are in the standard form, which number 1, 2, 3, 4, but 5 is not in the standard form. In equation number 1, this 1 upon x dx and cot x is dx, y is first side, we write just cot x into y, dx into y, cot x is equal to p of x, in this equation px tan x, in this situation no function, only y is going to be considered as plus, then minus 1 as p of x, only y you can write dy by dx plus then bracket -1 then y. So -1 considered as p of x by comparing the general form. Then this equation is not a standard form. If you write this equation in standard form, so first d 2y minus 3x, then x dy by dx is equal to 0. Then x dy by dx plus 2y, then x is a right hand side function because right hand side involve only function of x, then divide whole equation by x dy by dx, then 2 upon x, y is equal to 3. So this is a standard form, dy by dx, then this is p of x, then y power 1, and this is q of x. So you can easily solve. If equation is not maintained dy by dx operator and identified by dx by dy, so you just try to solve by dx by dy only the change in u into v formula. V is equal to x and the remaining situation is same. Thank you.